she got her PhD at the University of British Columbia, then did a couple of postdocs. One was the Torres Fellow. She was a Torres Fellow at MIT, and then she was a TESS postdoctoral associate also at MIT. But now she's back as assistant professor since July, I just found out, at UBC. So, and we're going to talk about the demographics of exoplanets, and that's and so I'll let the professor take it from here. Thank you so much for connecting, and we'll anybody has a question online or otherwise, just shout out, especially the ones online, because we don't necessarily have control over the chat. All right, take it away, Professor.
Okay, sounds good. Yeah, thank you so much for having me. And I really love exoplanets. I've been working on it basically since I was an undergraduate student. And I think one of my favorite things about exoplanet astronomy is just how it's an incredibly fast-growing field. We only knew of the very first exoplanets about 30 years ago, and it's just become such a rich area of expertise. So there's a few questions that kind of motivate the work that I do, and also especially motivate the demographics work that I do. And I'll talk about what demographics actually is in a bit. But the first motivating question I just accidentally flashed up really quickly there is kind of a question that everybody has probably asked themselves at some point in their lives. And that's the really big question of, are we alone? Is there other life out there? Where might it be? If there is other life, it would likely exist on another planet. And so by searching for more planets, we can try to start this really long investigation path to understand exoplanetary habitability. I think that the reason I chose this photograph is the famous pale blue dot image. And I think better than any other photograph, it really captures that sense of curiosity we have to understand our place in the universe. And it's not just a scientifically interesting question about how common other Earths are there, but also a philosophically interesting question as well. But more generally, how did we come to be? How did our solar system evolve and form? Is it really easy to form planetary systems like ours, or are we really rare in the universe? Now, there's all sorts of physical processes that dictate how planets form and evolve, which is really getting into the physics of astrophysics. And I'm really interested in understanding all of those processes, and so we can understand the diversity of planets we see today. So specifically, I try to answer these two really big questions, the kind of are we alone question and the how did we come to be question, through exoplanet demographics. So demographics is kind of like doing a demographic survey of people in Canada and in the US, but instead of surveying people, we're surveying exoplanets. There's different trends that we see in our planet populations, which types of planets are more common than others. And all of those physical processes that dictate planet formation and evolution are imprinted on those trends. So what demographics does basically really big statistical studies or population studies of exoplanets. Now, specifically what demographics studies try to answer is what is the occurrence rate of planets? Now, some people have different definitions of what they mean by an occurrence rate. So for this talk, I define an occurrence rate as the number of planets per star. It's basically an overall abundance of exoplanets. And so if we go back to that first motivating question, are we alone? What we can ask demographics is, what is the occurrence rate of potentially habitable Earth-like exoplanets? Now we have to understand what we mean by Earth-like. And typically when we say potentially habitable, we mean it's in the habitable zone of its star. It's the range of distances from a star where a rocky planet can host liquid water on its surface. But this is a type of question that we can actually estimate to give us a better sense of the potential for habitability in our galaxy. But we don't just look at the overall number of planets per star, we can also look for trends in those occurrence rates. Do occurrence rates depend on different planetary system properties like planet size, planet mass, orbital period? Is it that planets that are really big are more common, planets far out versus close in? And how do these depend on stellar properties? Is it that high metallicity stars have more planets, low metallicity stars, old stars versus young stars? All these different trends that tell us how planets form and evolve are going to be shaping these really important occurrence rates. And so demographics really gives us a ground truth data set that we can use to test our theories of planet formation and evolution. So for this talk, I'm going to give a brief outline about how you actually do a demographic study, what we have to take into account when we're studying exoplanet demographics. I'm going to cover some major results from the Kepler mission, which was NASA's first ever exoplanet finding mission, and also to date, our best data set for understanding demographics. I'll cover some of the work that I've done with TESS to push the demographics into new frontiers with this new data set. And then I'll start talking about some of the future directions that I want to take the field. Okay, so I already mentioned that demographics is basically a really big population study of exoplanets. And what we know so far is that there are about 6,000 confirmed exoplanets and several thousand more planet candidates, which are not confirmed for various reasons, but we still nevertheless believe are planets. But here I'm just showing a planet mass versus orbital distance diagram of all the confirmed planets we know of so far. And I've also color-coded them by different detection methods because different methods have been used to find exoplanets over the past 30 years. I've also plotted the solar system planets in white, so you can kind of see where exoplanet discoveries are in relation to our solar system. So already just by looking at our observed planet population, we can see that there are overdensities and underdensities, and some planets are clearly more common than others. And this tells us something about the efficiency of planet formation and the types of processes that go into all those different formation mechanisms. So just a few major populations that have drawn a lot of interest to highlight. You'll notice that there's this really big clump of planets down here. These are the relatively low mass, relatively close-in planets. Because of their size, we consider these super Earths and sub-Neptunes, so just a little bit larger than the Earth, but still primarily rocky, and a little bit smaller than Neptune and primarily volatile rich, like the giant planets in our solar system. And what's interesting about this class of planets is that these are the most common size of planets that we've ever found. And yet our solar system actually lacks a planet with these properties. There's no planet in the size range between Earth and Neptune. And that's actually an open question within exoplanet science. Why do we lack the most common type of planet? And it's one of the reasons why our solar system is kind of rare. You'll also see that there are these two big clumps of giant planets. So Jupiter mass planets that are extremely close in. So they orbit their stars in just 2 days, 3 days. These are called hot Jupiters because they're so hot because they're so close to their stars. And the analogous cold Jupiter population, more similar to the Jupiter in our solar system. All right, so if we were to look at this population and start to ask things like what planets are more common than others, seems like planet formation really likes to form small planets as well as hot Jupiters. It doesn't really like to form warm Jupiters and cold Jupiters. And I wish it was that simple. But I do want to place a really important caveat whenever we're looking at our observed planet populations. And some people maybe don't realize that what demographics is actually doing is understanding how this data set is extremely biased. So it would be kind of like if you were, let's say, going to a sports game and you start asking people, are you a sports fan? You're probably going to get a lot of people that say yes. And so that's a very biased survey that you're performing. And so similarly, as we're surveying different stars to find exoplanets, we're probably going to get the planets that are really easy to find more often than those that aren't easy to find. And so they're going to be overrepresented in our observations. So a really big part of demographics is taking our observed planet populations, correcting for those biases so that we can actually reveal the underlying population of exoplanets. Not only are some planets more easier to find than others, but every survey, every detection method has its own unique sensitivities. For example, if you look at the light blue planets on the left-hand side from the transit method, which I'll talk a little bit more about later, you'll see that most of them are within 1 astronomical unit. So they're within the orbit of Earth. Whereas planets on the top right-hand corner here, direct imaging planets. So these are planets that are literally imaged. We have a picture of these exoplanets. These are really, really massive planets at the largest separations. And so these are completely different planet populations, and there's no single survey that can tell us everything. So typically when we're doing a demographic study, because of all these issues, we have to focus on just a single type of survey, a single type of detection method, and really understand the biases present in those surveys. Now, these problems are pretty much why we don't see any planets below this red line. It's not the planets here don't exist. It's just that they're so hard to find that they're going to be underrepresented here. Now, unfortunately, you'll see that most of our solar system is in this, but this actually makes me really excited because it tells us just how much more we can learn about exoplanets. All right, so keeping in mind that we have this bias data set, we have to understand, how do we debias our observations? This is where NASA's Kepler mission came in. So Kepler was NASA's first ever exoplanet finding mission. It launched in 2009 and it lasted for 4 years. And it was specifically designed as a demographics mission. And not only as a demographics mission, but specifically it had the precision to find small Earth-sized planets around sun-like stars in year-long orbits. And this was the first mission capable of doing that. And even to date, it's unique in its incredible precision and its observing strategy of looking at all these stars for 4 years. So it looked at about 150,000 stars simultaneously, looking at every single one of these stars and recording a measurement of its brightness every 30 minutes for 4 years consecutively. So the way that Kepler found planets is also the method that I primarily use in my work, which is the transit method. And the idea behind the transit method is if you happen to be looking at a faraway planet orbiting around its star and it happens to pass directly between you, the observer, and the star itself, it will block a little bit of that star's light. And so you'll see a temporary decrease in the observed brightness of that star. And because planets complete their orbits once an orbital period, we'll see those transits repeat very periodically. It also gives us a sense of how big planets are, because a really big planet is going to block a lot of light, and a small planet will block a little bit of light. And so Kepler was able to do this transit method on all these 150,000 stars. And just to give you a sense of how successful Kepler was, this is a plot of planet sizes or radius versus their orbital period, so how long it takes for them to orbit their stars. And this was all the transiting planets known before Kepler. You can see that there are a lot of these hot Jupiters, the really big planets at very short periods. And Kepler completely shaped how we saw exoplanets. It really filled in the small exoplanet parameter space that we didn't have access to before, while giving us this incredibly rich data set to go through for demographics. So Kepler found 2,700 confirmed planets, which is about half of all of the known exoplanets we know today. And it also found another 2,000 candidate planets. So overall, about 4,700 planets and planet candidates that we can dive into for understanding exoplanet demographics. So there's a lot of various biases that are present in transit surveys and Kepler especially. And if you have any questions about any one, I'm happy to go more into detail, but I wanted to kind of skip to some of the science. So essentially what I've done here is on the left-hand side, I've taken those 4,700 planets and planet candidates from Kepler, and I've split them up into a grid where each grid cell represents a small area of planet radius orbital period space. And in each of these grid cells, I have an understanding of how biased our survey is. So planets that are really, really big, have really big transit depths, and those that have short periods, so they have a lot of transits, are going to be way easier to find than planets in the bottom right corner, where it's, these planets are so small, they have tiny, tiny transits, they take forever to orbit around their stars. And so once we understand all those biases, we can then correct that, debias it, and we get something like this on the right-hand side. This is an occurrence rate grid, and it represents our bias-corrected number of planets per star. So just to kind of summarize some main takeaways, in green are the more common types of planets. So you can see there's a lot of super Earths and sub-Neptunes. In red are the least common types of planets, and in gray are boxes where we don't actually have any detections at all, so we can at least place an upper limit on their occurrence rates. All right, so if we go back to that very first motivating question, the are we alone question, I said one thing we can ask demographics is, what is the occurrence rate of Earth-like planets in the habitable zones of sun-like stars? So this abundance is also known as eta Earth. So I'm going to use this term eta Earth a few times. Essentially, it's how common other Earths are. So if we turn to our nice bias-corrected occurrence rate grid and we ask, well, where is Earth on this? Can we estimate the occurrence rate of other Earths? unfortunately, we would see that Earth lands right in this gray region where there weren't actually a lot of detections from Kepler. So this is actually somewhat interesting because Kepler was designed to find these types of planets, and it spent 4 years trying to find them, but it was actually supposed to last for a lot longer, and it ended its mission early due to instrumental failure. And so it didn't actually reach its primary mission goal of finding enough Earths to confidently measure this eta Earth value. So in some respects, it is, I mean, I'm not the person who said this. I have a friend who works at NASA who was on the Kepler mission. He said the Kepler mission was a failure because of this. I don't agree with them because it gave us this incredible array of demographic knowledge, but just to kind of show the challenge of estimating this eta Earth value. Another issue about estimating eta Earth from Kepler is that the habitable zone, so that range of distances from a star where a planet could have liquid water, for sun-like stars, it extends out to 800, 900 days in orbital period. And Kepler only had sensitivity out to about 400 or 500 days, given its 4-year data set. So not only do we have to extrapolate from regions where we have occurrence rate information to get an eta Earth estimate, we also have to extrapolate well beyond Kepler sensitivity. Kepler still remains, despite all these issues, our best data set for understanding this eta Earth number. And if we were to plot all of the eta Earth estimates from Kepler on a single plot, you would see that they range across 3 orders of magnitude, kind of reflecting that challenge for estimating it. But it is the best we can do so far. So what I'm showing is a chronological retelling of all of the eta Earth values from various studies. And you can see that on the absolutely most pessimistic end, there's maybe 0.01 Earths per sun-like star. And on the absolute optimistic end, there's maybe 4 Earths for every sun-like star. Now, for the work that I did as a grad student, and then eventually, while I was a postdoc, I collaborated with the Kepler team to come up with their final best estimate. We said, I think it's more like about 0.5. So for every 2 sun-like stars, there is an Earth-like exoplanet that is in the habitable zone. So if there's hundreds of billions of other sun-like stars, then that could mean hundreds of billions of planets that have similar basic properties as our Earth. So one thing I want to mention, though, is that understanding this eta Earth, this abundance of other Earths, isn't just this warm and fuzzy kind of are we alone question that we're trying to address. It's also crucial to understand this so that we can best design future missions that are designed to find and characterize other Earths. And one of the most important ones in the foreseeable future for astronomy is the Habitable Worlds Observatory. So there's a survey that's basically done of the astronomical community every decade called the Decadal Survey. And astronomers are asked to say what they believe should be the priority for astronomy over the next decade. And this influences a lot of the work that NASA does, where it spends its money, basically. And out of the Astro 2020 Decadal Survey, loud and clear, astronomers said that the search for habitable worlds should be the top priority. And as a result, NASA selected the Habitable Worlds Observatory as one of its next major flagship missions. So this is going to actually directly image and search for biosignature gases in the atmospheres of other Earths around sun-like stars. And hopefully it'll launch in about the 2040s. So we're at the point where we're now trying to design that mission. We're trying to figure out, how big of a telescope do we need? Where are we going to spend these multi-billion dollars to build this telescope? And a lot of that hinges on how well we understand eta Earth. So this is a plot that was included in the Astro 2020 Decadal Survey, and it shows how many Earth-sized habitable zone planets that we expect to find if we looked at 100 stars with the Habitable Worlds Observatory, depending on how big of a diameter the telescope actually has. So they adopted one of our more conservative estimates, which is that 1 in every 4 sun-like stars has another Earth. And if we were to assume a 6-meter class telescope for this a final mission design, and we look at 100 stars, then you would expect to find about 25 other Earths. But there's a more recent estimate that said that eta Earth is more like 7% of all sun-like stars, and the error bar is pretty large, and so we're within 2 sigma of 0. So it would be a real shame if we spend billions of dollars on a 6-meter class telescope expecting to see 25 Earths, and maybe we see just 1 or 2. So the Eta Earth issue is a really big issue. It's an open issue in the field right now. There's a lot of efforts trying to improve Eta Earth, recognizing that Kepler is still our best data set to do this. And one such effort that I'm part of is to fully reprocess the entire Kepler dataset with better stellar properties and better techniques for making light curves and doing planet searches. And hopefully we can start to fill in some of those really small Earth-like planets that were missed by the original Kepler pipelines. But we should be able to start to improve on this number. So definitely keep an eye out for improvements to Eta Earth over the next few years. Hopefully we'll get there. But Kepler was not a failure. I mean, it gave us some incredible data beyond just the Eta Earth issue. It gave us all this demographic information for planets across all sizes and orbital periods up to 400 days. And these trends tell us something about planet formation and evolution. So what I'm going to do now is I'm going to highlight some major trends that I find most interesting. I won't be able to cover everything Kepler told us, but some of the things that mostly I've worked on. So one feature I want to draw your attention to is this kind of paucity of planets on the top left-hand corner here. So you'll see that there's clearly a dearth of planets that are intermediate in size, so roughly the size of Neptune. And we have hot Jupiters at these orbits, and we also have hot rocky super-Earths at these orbits, but we don't have Neptune-sized planets. And this is a de-biased occurrence rate grid, so we know that it's not because hot Neptunes are hard to find. This is an intrinsic lack of planets that are intermediate size. So is there something in our theories about planet formation or evolution that can explain why we don't have specifically intermediate mass planets at these really short orbits? So kind of the favorite explanation that especially explains the lower bound of this so-called Neptune desert is a process called photoevaporation. The idea behind photoevaporation is that if you have a planet that has a nice thick atmosphere, but that atmosphere is bombarded by an enormous amount of XUV radiation because the planet is so close to its star, the atmosphere is going to be ionized and it could actually be completely stripped. It'll escape from your planet itself. And so over time, especially in the first billion years after planet formation, a planet can be completely stripped of its atmosphere and basically become a bare rocky core. So the idea is that you'll have planets that maybe were intrinsically born in the Neptune desert, but over time, they lost their atmospheres due to this mass loss mechanism, and they now have become the smaller super-Earths that we see in today's very evolved Kepler population. And the reason we see planets that are as large as hot Jupiters still able to hold on to their atmospheres at these short period orbits is just because bigger planets mean they have more mass. More mass means more gravity. It's able to hold on to that atmosphere and resist photoevaporation much better than the hot Neptunes. And meanwhile, planets down here either were intrinsically born rocky, like our Earth, or they were originally hot Neptunes that have since had their atmosphere stripped. Another really important feature I want to highlight is what's called the radius valley. This is probably the most discussed feature in small planet demographics from Kepler. And it's essentially a bimodal distribution of planet sizes. So if you just plot planet sizes as a histogram and then take a debiasing of these, you'd see that there's a peak at about 1.3, 1.5 Earth radius, a peak at about 2.5 Earth radius, the sub-Neptunes, and a valley in between those two centered at about 1.8 Earth radius. Now, this is a really cool feature because there are many theories that explain it, from planet formation, just in the earliest days of a planetary system's formation, and all the way through planet evolution. So over the next billions of years, there's a lot of mass loss features that can explain this. There's planet formation theories that explain this, and all of them too probably an equally good job of explaining the same feature. And so we're still not entirely sure what process is dominant in forming this radius valley. One of the favored features, explanations, is the photoevaporation process that I just mentioned, where planets that are kind of the sub-Neptune class aren't able to hold on to their atmospheres due to the radiation, and then they drop and they become the super-Earths over here. You can also just take a histogram of orbital periods and debias them. Let's see what happens. And so this is what happens when you take small Earth-sized planets and super Earth-sized planets, and you take a look at how their abundance changes with orbital period. So we see that planets are really, really rare, really close to their stars, and they kind of increase in occurrence out to about 10 days in orbital period. And then we have this fall off, or roughly flattening out of the trend. So once again, this is basically telling us something about planet formation or evolution. In order to explain this trend, we can come up with a story. So the favored one that I've come up with is kind of based in the earliest days of planet formation. And this is a very toy model of planet formation, but it works well for this scenario. So essentially, when a planet is forming, it's forming in what's called a protoplanetary disk. It's the swirling disk of gas and dust around a star. And this is a real life example of an actual protoplanetary disk. Now, this protoplanetary disk doesn't reach all the way to the star itself. It has this truncation at some point, and you can't have planets forming within the truncation radius. And so one open question is, where is the truncation radius? How close can you actually form exoplanets? And one of the favored reasons for why we have a truncation radius is it happens around where we have this co-rotation radius. It's essentially the radius where any orbiting object has the same orbital period as the rotation period of the star. And so if the co-rotation radius is really important for deciding how close planets can form, if we take a histogram of stellar rotation periods, so that would be corresponding to the co-rotation period, we see that they have a slope that follows the slope of the Earths and super Earths really, really well. And it peaks right at about 10 days, which is exactly the turnover that we see in the small planet population. So this is an example story where even though Kepler's planets are many billions of years old, the trends that we see in those populations can still have imprints and leftover imprints of the earliest days of planet formation. And any theories of planet formation or subsequent evolution of small planets has to be able to explain these types of features. You can also do the same while looking at larger planets. You can see that they all have unique orbital period dependence. Some of these could be due to formation. Some of these could be due to subsequent migration or evolution. There's a lot of different things that go into why planets look the way that they do. But the point is that we're providing ground truth data sets that you can use to test those types of theories. So just to kind of summarize everything that I've talked about from Kepler, the major highlights. The occurrence rate of exo-Earths we think is maybe about 0.5, but it could be 10%, it could be 100% of stars. Sun-like stars have other Earths. There's a lack of consensus, and that's a big open question right now, is how do we improve on the eta-Earth estimate? Some trends that we see are left over from planet formation, and others are very sculpted by subsequent planet evolution. And if you were to add up all of the planets that we see in our occurrence rates from Kepler, at least within the 400-day sensitivity from Kepler, we would see that on average, every sun-like star has about one planet, and probably more. So Kepler was great, and this is just a quick summary of the major takeaways that Kepler gave us. But I'm also interested in another very special mission, and it's almost completely underutilized for demographics. And I'm, of course, talking about the TESS mission, which is where I worked as a postdoc for 4 years. So TESS is NASA's current exoplanet finding mission. It launched in 2018, and it is still ongoing. It's still observing the night sky. And where Kepler decided to look at the same 150,000 stars for 4 years, TESS took the very opposite approach, which is quantity over quality, essentially. Instead of having the amazing precision that Kepler had to find other Earths, TESS decided on focusing on an enormous field of view. So it looks at about 1 million stars every month. Now, TESS looks at these sectors of the night sky. These are huge strips of the night sky. So it's got this enormous field of view. And it looks at these sectors for 27 days at a time before rotating to look at the next sector. And after an entire year, it has been able to map out basically an entire hemisphere of the night sky. And as TESS has continued to observe, we've been filling in the gaps left behind previous years. We've been re-observing sectors that got data in the past, and we've been able to find a lot of exoplanets. And what's really great about TESS for demographics, so even though it wasn't designed as a demographics mission like Kepler, and it has a lot of challenges for doing demographics because every star has a unique amount of data. The precision isn't as good. There's some issues. What's great about it is that it has no pre-selection of targets. If a star happens to land in your field of view, we have data for it. And so TESS can give us demographic information for not just sun-like stars, but all types of stars, evolved stars, young stars, metal-rich stars, metal-poor stars. It could even tell us about exoplanet populations around white dwarfs. TESS found the very first and so far only known transiting exoplanet around a white dwarf. So there's a lot of detail here that we can understand about planet populations around non-sun-like stars, thanks to TESS. So if we look at the types of planets that TESS found compared to Kepler, we see that Kepler was really great at finding these small planets because it had that incredible precision to find other Earths. And so it found 4,700 planets and planet candidates across hundreds of days of orbital period for sun-like stars. Meanwhile, because TESS is more focused on looking at a large number of stars for much less time, it's really good at finding the easy to find planets, the hot Jupiters. And so that's why you can see there's this enormous number of hot Jupiters in the top left corner here. It has also found some small planets, especially around M dwarfs. So one thing I want to mention is a lot of the work that I do is to try to improve TESS's application to demographics, and that means giving us even bigger planet catalogs, which we can use to dive into demographics. And so about half of all the TESS planet candidates have been found by what I call the faint star search. This is something that I lead out of UBC, and it's a collaboration that I do with the TESS team since I've left to try to identify new planet candidates. So just to quickly mention how the faint star search works in case anybody here is interested in getting involved in their own planet searches. The faint star search is essentially addressing a really big issue with the TESS demographic field right now, because TESS planet searches involve a lot of manual inspection to identify planets. And human decision-making is an extremely biased process. And that's one of the reasons why there aren't a lot of demographics projects working these days out of TESS, because it was never designed to support demographics the way Kepler was. So one of the things that I've done is I've designed this very automated planet search that removes the need for manual inspection to identify new planet candidates. So we have much more uniformly vetted planet catalogs. And this specific pipeline that I've developed is called LEO, standing for Lazy Exoplanet Operations. It's available on my GitHub if anybody wants to use it for their own planet search, any of their planet search desires. But essentially what it does is it takes planet candidates that are found and it separates them into various classes of objects, the planets, which is what we're interested in, eclipsing binaries, which are stars, because they can also cause transit-like events, and a third class of objects, which sometimes we pick up a lot in our transit searches, which are just random noise fluctuations, instrumental systematics, stellar variability, basically non-astrophysical objects that can cause transits. Now, I don't know if anybody here is a football fan, but I named Leo after the sports mascot of my favorite football team, the BC Lions. It's Leo the Lion. So yeah, I'd encourage you to use it if anyone's interested in searching for their own planets. But back to demographics. So I mentioned that TESS has kind of been underutilized for demographics, and a large part of that is because TESS planet searches have largely been manually, they've been done with an automated planet search, but then there's a lot of manual inspection that goes into identifying the final planet candidates. And so a lot of the TESS demographic work so far has focused on the really easy to find, easy to distinguish by eye exoplanets like the hot Jupiters. So these are some highlighted results from TESS demographic literature so far. What we see is how the hot Jupiter abundance changes with stellar mass. So we have G dwarf stars, our sun-like stars, seem to be the most common hot Jupiter hosts. And so hot Jupiters orbit about 0.5% of all sun-like stars. But then we see there's this fall off where the larger, hotter stars, A-type stars and F-type stars, have lower hot Jupiter abundances. And the M dwarfs on the opposite side, the really low mass types of stars, they also have really low hot Jupiter abundance. So it's kind of interesting how there's not a clear monotonic trend with stellar mass that explains the population of hot Jupiters that we see today. So one explanation for the low abundance of around A-type stars is that there's a tidal disruption. So when these planets are so close to such large, massive stars, it's much easier for them to be torn apart by tidal forces because of the high masses of their host stars. So you can't really have a lot of planets super close to these really high mass stars. On the other hand, these very low mass stars are not likely to be corresponding to protoplanetary disks with a lot of materials, because generally the amount of material that you have available to you scales with the host star that you have. And so there's not a lot of giant planets around M dwarfs simply because there wasn't enough planet forming material to make them. And even just a few years ago, we had basically no discoveries of Jupiter-sized planets around M dwarfs at these close-in orbits. And TESS is only starting to find the first examples. And that's already causing us to change some of the ways that we see planet forming around M dwarfs because we didn't expect them to be possible. And one more feature that I want to highlight from TESS demographics so far is just that because we're looking at non-evolved sun-like stars, TESS can paint a picture of how planets change over time. So what I'm showing is different occurrence rates for very close-in Neptune-sized planets. So that's corresponding roughly to the hot Neptune desert. And we saw that from Kepler, that number was relatively low. We also have data from TESS, which are for tens to hundreds of million-year-old planets, so very, very young planets. And we can see that the hot Neptune abundance used to be a lot higher. And so we can start to ask ourselves, is there some story we can tell that explains why we see these trends that fits with our understanding of planet formation and evolution? So the basic story that can explain these types of results are that originally we have planets forming in the hot Neptune desert or near it, in the first few millions of years of the planetary system. We then have an increase of hot Neptunes. So the hot Neptune abundance is actually increasing over the next hundreds of millions of years. And one possible mechanism is that planets are moving inwards. They're migrating inwards from farther out orbits, and they're starting to fill up the Neptune desert through tides. But then we see that abundance starts to drop off rapidly, or I guess over the next few billions of years. And so something is causing the Neptunes to now leave the desert. And that's where that atmospheric mass loss probably comes in. It's causing those planets to be losing their atmospheres, and now they are the evolved, much lower abundance of Neptunes that we see so far. All right, so there's one more type of population that I want to highlight from TESS, and I'm going to put a question mark next to it because it's something that I've been kind of throwing around as an idea over the last year, but it's very untested, and so who knows what's going to happen. But I think that TESS can also tell us about the population of not just bound stars around diverse stellar populations, but also rogue planets. So rogue planets are also called free-floating planets, and these are planetary mass objects that don't orbit any star at all. And if you actually look at the International Astronomical Union definition of a planet, technically they'd say that these types of planets these aren't actually planets because they don't orbit a star. But I'm going to call them rogue planets for the sake of communication. So there's two major pathways for having a rogue planet. One is that, especially the larger rogue planets, they were just failed stars that never became forming stars and formed their own planetary systems. But a lot more of them, probably like the terrestrial mass rogue planets, probably formed originally in planetary systems, much like our own solar system. But in the early chaotic days of solar system formation and evolution, they were thrown out of their system and they are now freely floating throughout the galaxy. And so far, just in the past 5 years, we have found the first ever terrestrial mass free-floating planets. And that's mostly from, those are all from ground-based surveys that have been looking at the sky for decades. And based off these discoveries, we believe that rogue planets there's about on order 10 rogue planets for every sun-like star. So these could be a lot more common than bound planets around different types of stars. But I was thinking, well, one of the ways that we find rogue planets is through this technique called microlensing. And the idea behind this is that a planetary mass object or any massive object bends space around it due to its mass. And if this object passes directly in front of a background star, what happens is that the light from that star will be bent around your massive object. and it will be imaged onto what's called an Einstein ring, which essentially results in the background object looking brighter for a few hours as this object passes by. So what this gravitational microlensing looks like is this spike in brightness. So if TESS is really good at finding decreases of brightness caused by transits, surely it can also find increases of brightness caused by microlensing events. And because TESS is an all-sky survey, it's going to be able to look for microlensing events across the entire sky. Now, microlensing events require this very rare alignment of objects, and so we need really, really big stellar samples to look at. And TESS is looking at millions of stars every month, and so it could be a really great survey to do exactly this, to better understand the rogue planet population. And if we compare it to ground-based surveys, partly because the size of the telescopes and the limitations of being on the ground, mostly ground-based surveys are sensitive to 10% increases of brightness, while TESS is sensitive to an order of magnitude smaller changes of brightness. And the cadence of ground-based surveys is typically about 15 minutes or more. So they record measurements of brightness every 15 minutes. TESS records measurements of brightness every 200 seconds. And so it's able to find much shorter duration microlensing events, which are exactly the regime of the low mass terrestrial free-floating planets that we hope to find. So I started by thinking about how I would take kind of the faint star search that I did with all that automated planet detection for transits and turn that into a microlensing planet detection algorithm. And there's a lot of ways that microlensing false positives manifest. So these are things that can cause a star you're looking at to increase that are not caused by microlensing. There's stellar variability, of course. There's cosmic rays, which are single cadence increases of brightness. And especially problematic are flares. So these are just indications of stellar activity. A star will typically very quickly get bright and then kind of have this exponential fall off due to magnetic activity. There's also scattered light. So every TESS orbit, so every 2 weeks, light from the sun will scatter off the surface of the Earth into the TESS cameras and cause this huge increase of brightness. So every 14 days, you expect to see a really big brightness increase. You can have heartbeat stars, which are binary star systems where when they get very, very close to each other, you have this periodic pulsation where the brightness of the system increases. And you can also have just asteroids. If any of them are reflecting light from the sun as they pass by close to the star that we're looking at, you can see an increase of brightness due to that. So there's a lot of things that you have to consider when you're designing a microlensing search. Asteroids I want to highlight just because they were one of the most common types of false positives. I originally, of course, because I didn't really know much about microlensing when I started this, I got really excited. I was finding all these nice, relatively symmetric one-time events that were big brightness increases, and they all turned out to be asteroids. Typically, you can cross-match your detection with JPL's small body database, and it will tell you if an asteroid that it knows about passed by at the time of your event, and sure enough, the vast majority of my signals failed. This was actually a case where we had an event that didn't appear to be in the small body database, but if you look at the actual TESS pixels at the time, I've subtracted out all the stars from this image, and so all you're looking at is the pixels that are changing in brightness over the timescale of the event. And so clearly there's something moving across the field. I don't know exactly what it is, maybe a near-Earth asteroid, but clearly it's not a microlensing event. However, after searching about 1 million stars, so just a single sector of TESS observations, we found one candidate that didn't fit any of the false positives that we looked at. It had a nice symmetric profile. It was very well fit by a microlensing profile. And so this could be TESS's first microlensing free-floating planet candidate. That said, these are extremely rare events, and we only expected to find maybe one out of all 70 TESS sectors that were observed at the time. So we were very concerned that, like, what's going on here? Clearly we must have messed up or something. So maybe it's not a rogue planet, and it's this weird class of microlensing false positives that we clearly don't understand very well, because all of the typical ways to get rid of false positives failed for this particular event. And this has huge implications for NASA's Roman telescope, which is launching in a couple years. And it's going to be doing something like what TESS is doing, looking at a large part of the sky looking for these microlensing events. And so this is a motivation to better understand microlensing false positives before Roman. Or it is a rogue planet and we were either extremely lucky to find it, or rogue planets are even more common than we expected. And that has implications for the types of planets that are being thrown out of systems early in planet system formation and evolution. So just to close up here, because I know I'm running out of time, some major areas I think that TESS can really improve our understanding of demographics, given it is so early in the field. Definitely focusing on the giant close-in planets, that is his specialty. We can estimate the first ever white dwarf exoplanet occurrence rate with an actual detection of a planet around a white dwarf. We can look for trends and correlations between planet abundance and the really diverse stellar sample that TESS is giving us, thanks to the Gaia mission giving us stellar characteristics. We can use TESS to better understand rogue planet abundance. And even if our event is a false positive, then that also tells us something about how false positives can manifest when searching for rogue planets, which has implications for NASA's Roman telescope. And if we look at all the types of planets that we've really understood through Kepler and through TESS and through the major demographic studies so far, if we were to place our understanding of exoplanet populations relative to the solar system, you would see that we're just getting started. We are really good at understanding demographics of small, close-in planets, but there's an enormous there's an enormous parameter space that we haven't even been able to touch yet. And as we continue to find more exoplanets, we'll be able to better understand even more of the exoplanet population. And if I bring us back just finally to this plot I showed you before about how we can look for trends in exoplanet populations, Roman is one telescope that is going to be giving us an incredible amount of information across all planet masses and orbital distances that is really complementary to the transit surveys that we've already been diving so much into. The transit survey from Roman is expected to find hundreds of thousands of exoplanets and thousands of microlensing events corresponding to bound or free-floating planets. So it's really going to help us understand. We're really at the tip of the iceberg in terms of what we can learn from this very young field of exoplanet demographics. So with that, I'll leave up my summary slide and I'll take questions.
I got confused about this inner edge of the accretion disk.
Uh-huh.
I was confused because of type 1 planet migration. So that's when you have a heavy disk and the viscosity just sucks everything in to the star. And so but if there's an edge to that, then how does stuff get on the star? So that's my that's my confusion. And that's
you can have material that is interior to the truncation disk, but that's not necessarily where planets can form.
Oh, it's hot or gas. Gotcha. Okay. Well, that clears everything up in one sentence. Thank you. What else? What's the question? Yeah.
Thank you very much for the talk. I was just wondering, so say that you actually do have a rogue planet every 5 test sectors, let's say. And so if you do some calculations, like considering the alignment that you need and so on and so forth, would they end up being like more than star orbiting planets, less than that? Like,
yeah, so actually your estimate of 1 per 5 sectors is really good because we were concerned about finding it in our first test sector, we looked at another 4 test sectors and we didn't find anything. So at the moment, we're at 1 detection per 5 sectors. We have plans to continue the search and see if that changes, but at the moment, we're at about 1 out of every 5. So if you look at the types of the expected yield that we had for exoplanets around for these free-floating planets, the current best estimates based off of the 3 detections from ground-based surveys is that there are 7 plus or minus 7 free-floating planets larger than 1 Earth mass for every star. So we already believe that there are many free-floating planets per star. And the discovery of this candidate, if it is real, again, big question marks there, but if it is a real free-floating planet, then that would indicate that we're closer to the 7+7, so like 15, 20 rogue planets per sun-like star, rather than kind of the lower bound of that. So I think once we search more of the TESS data set, we have a better handle of our statistics, recognizing that this is just a single detection. And this is all in preparation for Roman, which will do a much better job than TESS ever will. But part of the motivation was just to better understand how to do microlensing searches with space-based surveys, because that's never been done before.
Awesome, thanks.
Also, Poisson statistics is counterintuitive, right? Whatever the average is, that's okay, but the most likely time to find it is right now. What else? Yeah, Peter.
So do we also expect that there are rogue planets that originated from the solar system, like ours, again?
Yeah, actually, if there's been a lot of models and simulations of the early solar system, and because we have big giant planets like Jupiter, giant planets are really good at throwing objects out. And there are simulations that show that we should have lost, many Earth mass objects from the solar system that never became final planets that we have in our solar system now, but could be freely floating throughout the galaxy as free-floating planets. So the types of information that free-floating planet abundance can tell us is just how much mass might be getting ejected from these early solar systems and early planetary systems. And that number could be really, really high.
Fascinating.
It's can't understand that, like,
Yep. Anyone on Zoom?
Yeah, well, okay. Maybe I can ask a question. Thanks for the very nice talk. Again, a rogue planet question. What can be the other mimickers, let's say? I mean, could it be a brown dwarf or a primordial black hole that could also create a similar microlensing signature?
Yeah, so my collaborator is from a dark matter background, and he was throwing around primordial black hole as a possible explanation for it. Just because they're theoretical, we didn't really talk about them a lot in the paper that we're writing, but that would be an alternative explanation. However, we've done a lot of discussions with the microlensing community, recognizing that we are not microlensing experts. Like, I do transit science, I know TESS, but we're trying to use TESS for microlensing for kind of the first time. And some people are on the side of, well, it was so rare, you can't have found a free-floating planet so early, so I don't know what it is, but it's not a free-floating planet. But there's another contingent of people who believe that it's a flare. So flares I did mention as a possible false positive. They kind of have these quick increases of brightness followed by gradual decays, but theoretically you could have a perfectly symmetric flare. And if you look at the light curve for our star with ground-based telescopes that have been monitoring, like the Assassin survey, you can actually see that our star does have a 40-day period, which could correspond to a rotation period. And that could mean it has star spots. And if it has star spots, then it probably is magnetically active. And so maybe it is just a really weirdly perfectly symmetric flare. That said, we did consider the flare interpretation, and we estimated the energy that would be released to explain such a large change of brightness, a 6% change of brightness over 0.4 days. That's the duration of the event. And those properties, the energy released would be more than an order of magnitude more energetic than the most energetic flare ever recorded. So we don't necessarily think that it's a flare, but there are still people who, like, it could just be a very strange, high energy, perfectly symmetric flare as a possible explanation. Another explanation I didn't mention was it could be a coronal mass ejection. I don't know. This is kind of, I'm in discussion with the Roman team about how we can distinguish between these different alternative explanations and how Roman might be able to improve on what we've done and learn from TESS. So yeah, I plan to do some follow-up of the star itself, and maybe we can get to the bottom of it.
Very interesting. Thank you.
Yeah, let's just check in. Jose had a couple of things on chat here. Is Earth an outlier, and are there any missions to find super moons? That's an interesting question.
Yeah, there have been a couple exomoon candidates, especially from Kepler, primarily out of David Kipping has kind of been a leader in looking for exomoons. So the idea is that if you have a transit that's happening, and if the planet has a moon around it, then you should see a secondary bump, much smaller bump, but a secondary bump due to the exomoon also blocking light from the star. And so there are a few candidates that people have that especially David Kipping's group has kind of put forwards. None of them are confirmed exomoons, and it's hard to say how confident we are that they are actual exomoons. There was a HST targeted survey to follow up some of these to see if they could see that exomoon transit again, and it wasn't able to, depending on how you process the data. But yeah, it is theoretically very possible.
Fascinating. All right, let's thank our speaker again. Thank you very much.